Functional description of a modular electrohydraulic wellhead control panel. An electrohydraulic wellhead control panel, WHCP, is a critical component in managing the operation of oil and gas wells. It integrates hydraulic, electrical, and electronic systems to monitor and control various wellhead functions, such as valve operations, safety systems, and pressure monitoring. A modular WHCP is designed for flexibility and scalability, allowing easy expansion and customization based on specific well requirements. Key functions. Valve control. Operates surface and subsurface safety valves, SCSSV, SSSV, choke valves, and other wellhead valves. 2. Pressure monitoring. Monitors annulus pressure, tubing pressure, and other critical pressure points. 3. Emergency shutdown, ESD. Provides automated shutdown capabilities in case of abnormal conditions to ensure safety. 4. Data acquisition and communication. Collects and transmits operational data to central control rooms for monitoring and analysis. 5. Hydraulic power. Supplies hydraulic pressure to operate wellhead valves and actuators. 6. Electrical power. Manages electrical power distribution for sensors, control systems, and communication devices. Design and construction details. Components. 1 hydraulic power unit. Function. Generates and supplies hydraulic pressure. Construction. Includes hydraulic pumps, electric or diesel-driven, accumulators, reservoirs, and control valves. Materials. Corrosion-resistant materials such as stainless steel for wetted parts. 2. Control modules. Function. Houses control electronics and PLCs for automation and monitoring. Construction. Enclosed in weatherproof, explosion-proof cabinets with appropriate ingress protection, IP ratings. Materials. Stainless steel or coated carbon steel for durability in harsh environments. 3. Valve actuators. Function. Hydraulically or electrically actuated devices for valve operation. Construction. Robust design to withstand high pressure and corrosive environments. Materials. Stainless steel, nickel alloys for sour service applications. 4. Instrumentation. Function. Sensors and transmitters for pressure, temperature, and flow measurements. Construction. Intrinsically safe or explosion-proof designs. Materials. High-grade alloys, Teflon coatings for chemical resistance. 5. Piping and tubing. Function. Connects various components within the WHCP. Construction. High-pressure, corrosion-resistant piping and tubing. Materials. Duplex stainless steel, Inconel for sour service. 6. Safety systems. Function. Emergency shutdown systems and fire and gas detection. Construction. Redundant systems with fail-safe design. Materials. Fire-resistant explosion-proof housings. Design considerations. 1. Scalability. Modular design allows easy expansion and customization to meet specific well requirements. Standardized modules facilitate quick assembly and integration. 2. Redundancy and reliability. Redundant components ensure continuous operation in case of component failure. High-quality materials enhance reliability and longevity. 3. Environmental conditions. Corrosion resistance. Use materials resistant to corrosion from seawater, H2S, CO2, and other harsh chemicals. Temperature tolerance. Designed for wide temperature ranges, including Arctic and desert environments. Ingress protection. Weatherproof and explosion-proof enclosures to withstand harsh environmental conditions. 4. Safety and compliance. Safety systems include ESD, fire and gas detection, and emergency power-off systems. Compliance. Adherence to international safety and environmental standards and certifications. Hatched installation aspects. 1. Site preparation. Foundation. Ensure a stable and level foundation for the WHCP. Access. Provide adequate space for installation, maintenance, and operation. 2. Integration with existing systems. Compatibility. Ensure seamless integration with existing wellhead equipment and control systems. Interfacing. Standardize communication protocols and interfaces. 3. Commissioning and testing. Factory acceptance test. Conduct comprehensive testing before shipment. Site acceptance test, SAT. Perform on-site testing and commissioning. 4. Safety considerations. Hazardous area classification. Install according to the classified zone's requirements. Emergency systems ensure proper installation and testing of ESD and fire and gas detection systems. Maintenance and best practices. 1. Regular inspections. Routine checks. Inspect hydraulic, electrical, and control systems regularly. Preventive maintenance. Schedule maintenance to prevent unexpected failures. 2. Spare parts and documentation. Inventory management. Maintain an inventory of critical spare parts. Technical documentation. Keep updated manuals and schematics for reference. 3. Training. Operator training. Ensure personnel are trained in the operation and maintenance of the WHCP. Emergency drills. Conduct regular emergency response drills. Codes and standards. 1. API standards. API 6 specification for wellhead and Christmas tree equipment. API RP14C, recommended practice for analysis, design, installation, and testing of basic surface safety systems for offshore production platforms. 2. ISO standards. ISO 10423, wellhead and Christmas tree equipment. ISO 9001, quality management systems. 3. IEC standards. IEC 61508, functional safety of electrical, electronic, programmable electronic safety-related systems. IEC 6007-9, explosive atmosphere standards. 4. ATEX directives. ATEX 2014-34 EU, equipment and protective systems intended for use in potentially explosive atmospheres. 5. NACE standards. NACE MR0175's ISO 15156, materials for use in H2S containing environments in oil and gas production. 6. OSHA standards. OSHA 29 CFR 1910, occupational safety and health standards. Conclusion. A modular electrohydraulic wellhead control panel is a sophisticated and flexible system designed to manage wellhead operations efficiently and safely. By incorporating advanced materials, robust construction, and adherence to stringent safety standards, these control panels ensure reliable performance in harsh environmental conditions. Proper design, installation, and maintenance are critical to the long-term success and safety of wellhead control operations. Specification details of control loops in a wellhead control panel, WHCP. Control loops within a wellhead control panel, WHCP, are critical for ensuring the safe and efficient operation of oil and gas wells. These loops can be categorized into open and closed loops, with specific functionalities for monitoring, alarms, and shutdowns. These control loops are typically managed via programmable logic controller, PLC, or a remote terminal unit, RTU. Open loop control. Definition. Open loop control systems act based on predefined inputs without feedback from the process output. Examples. 1. Valve positioning control. Function. Adjusts valve positions based on operator input or preset conditions. Control device. Hydraulic or electric actuator. Operation. Operator sets the valve position. The system executes the command without feedback on the actual position. 2. Chemical injection control. Function. Regulates the injection rate of chemicals into the well. Control device. Dosing pump. Operation. Operator sets the injection rate. The pump runs at this rate without feedback on actual chemical concentration. Specifications. Control device. Valves, actuators, pumps. Control signal. 4 to 20 milliamps, 0 to 10 volt DC. Monitoring. Visual indicators, local gauges. Feedback. None. Operator monitors system performance. Hack closed-loop control. Definition. Closed-loop control systems use feedback from the process output to adjust control actions, ensuring desired performance. Examples. 1. Pressure control loop. Function. Maintains wellhead pressure within a specified range. Control device. Pressure transducer. Control valve. Operation. Pressure transducer measures wellhead pressure and sends feedback to the PLC RTU, which adjusts the control valve to maintain the set point. 2. Temperature control loop. Function. Controls the temperature of the injection fluids or the wellhead. Control device. Temperature sensor, heater cooler. Operation. Temperature sensor measures fluid temperature and sends feedback to the PLC RTU, which adjusts the heater or cooler to maintain the set point. Specifications. Control device, sensors, pressure, temperature, actuators, control valves. Control signal, 4 to 20 milliamps, 0 to 10 volt DC, digital signals. Feedback, real-time sensor data. Set points, configurable via HMI or SCADA. Control algorithm, PID, proportional, integral, derivative. Internal monitoring alarms and shutdowns. Internal monitoring function, continuous real-time monitoring of critical parameters to ensure safe and efficient operations. Parameters monitored: pressure, tubing pressure, annulus pressure, surface safety valve pressure. Temperature, wellhead temperature, fluid temperature. Flow rate, production flow rate, injection flow rate. Valve position, status of safety valves, choke valves, control valves. Devices used: sensors, pressure transducers, temperature sensors, flow meters. Transmitters, for transmitting data to the PLC RTU. PLC RTU for data acquisition, processing, and control. Alarms function: alert operators to abnormal conditions that require attention or corrective action. Types of alarms: high pressure, low pressure, indicate abnormal pressure conditions. High temperature, low temperature, indicate abnormal temperature conditions. Flow deviations indicate abnormal flow rates. Valve malfunctions indicate issues with valve operations. Devices used: alarm indicators, visual and audible alarms. HMI SCADA displays alarm status and logs. PLC RTU monitors conditions and triggers alarms. Function: automatically shut down the system to prevent damage or hazardous situations. Types of shutdowns: emergency shutdown (ESD) activates in response to critical failures or safety breaches. Process shutdown activates in response to process deviations beyond acceptable limits. Devices used: ESD valves close to isolate the well and prevent flow. Executes shutdown logic and activates ESD valves. Sensors detect conditions that trigger shutdowns. Control via PLC or RTU. Programmable logic controller (PLC). Function: centralized control and automation, handling real-time processing and control logic. Capabilities: data acquisition, collects data from sensors and transmitters. Control logic, executes control algorithms, e.g. PID. Communication, interfaces with HMI SCADA for operator interaction. Alarms and shutdowns, monitors conditions, triggers alarms, and executes shutdowns. Remote Terminal Unit, RTU. Function: distributed control and data acquisition, typically used in remote locations. Capabilities: data acquisition, collects data from local sensors and transmitters. Control logic, executes local control logic. Communication, transmits data to central control systems, HMI SCADA. Alarms and shutdowns, monitors local conditions, triggers alarms, and executes shutdowns. Control loop specifications: pressure control loop, sensor, pressure transducer, range 10,000 psi, accuracy 1.1% fs. Actuator, hydraulic electric control valve, 4 to 20 milliamps control signal. PLC RTU, PID control algorithm, set point adjustment via HMI SCADA. Feedback, real-time pressure data to PLC RTU. Alarm, high-low pressure alarms. Shutdown, ESD if pressure exceeds critical limits. Temperature control loop, sensor. Temperature sensor, range 50 degrees Celsius to 150 degrees Celsius, accuracy 0.5 degrees Celsius. Actuator, heater cooler, 4 to 20 milliamps control signal. PLC RTU, PID control algorithm, set point adjustment via HMI SCADA. Feedback, real-time temperature data to PLC RTU. Alarm, high-low temperature alarms. Shutdown, ESD if temperature exceeds critical limits. Flow control loop, sensor. Flow meter, range 0 to 5,000 BD day, accuracy is 1%. Actuator, flow control valve, 4 to 20 milliamps control signal. PLC RTU, PID control algorithm, set point adjustment via HMI SCADA. Feedback, real-time flow rate data to PLC RTU. Alarm, high-low flow rate alarms. Shutdown, ESD if flow rate deviates significantly from set point. Conclusion: the control loops within a wellhead control panel, WHCP, are essential for maintaining safe and efficient well operations. By integrating advanced sensors, actuators, and control systems managed via PLCs or RTUs, these loops provide precise control, real-time monitoring, and automated response to abnormal conditions. Adhering to design specifications and incorporating robust monitoring, alarm, and shutdown mechanisms ensures the reliability and safety of wellhead operations. Control loops within WHCP for SCSSV, SSV, and ESD valves. A wellhead control panel, WHCP, includes multiple control loops to manage surface-controlled subsurface safety valves, SCSSVs, surface safety valves, SSVs, and emergency shutdown, ESD valves. These control loops ensure the safe and efficient operation of an oil well by monitoring and controlling various safety and operational parameters. Surface-controlled subsurface safety valve, SCSSV, control loop function. The SCSSV is a critical safety device installed downhole to shut off the well flow in case of an emergency. Components: hydraulic actuator operates the SCSSV. Hydraulic control line connects the WHCP to the SCSSV. Pressure transducer monitors the hydraulic pressure in the control line. PLC RTU controls the hydraulic actuator and monitors the pressure transducer. Operation: 1. Normal operation. The WHCP maintains hydraulic pressure to keep the SCSSV open. 2. Shutdown. In case of a high-pressure alarm, low hydraulic pressure, or manual ESD activation, the PLC RTU vents the hydraulic pressure, causing the SCSSV to close. Control loop. Closed loop. The pressure transducer provides feedback to the PLC RTU, which adjusts the hydraulic pressure to maintain the SCSSV in the desired state. Feedback: real-time pressure data from the transducer. Control signal: hydraulic pressure regulated by the PLC RTU. Surface safety valve SSV control loop. Function: the SSV is installed at the wellhead to provide a quick shut-off mechanism for the well flow. Components: hydraulic actuator operates the SSV. Hydraulic control line connects the WHCP to the SSV. Pressure transducer monitors the hydraulic pressure in the control line. PLC RTU controls the hydraulic actuator and monitors the pressure transducer. Operation: 1. Normal operation. The WHCP maintains hydraulic pressure to keep the SSV open. 2. Shutdown. In case of an ESD activation or high-low pressure conditions, the PLC RTU vents the hydraulic pressure, causing the SSV to close. Control loop. Closed loop. The pressure transducer provides feedback to the PLC RTU, which adjusts the hydraulic pressure to maintain the SSV in the desired state. Feedback: real-time pressure data from the transducer. Control signal: hydraulic pressure regulated by the PLC RTU. HASCRA emergency shutdown ESD valve control loop. Function: ESD valves are part of the safety system designed to quickly isolate the well in case of an emergency. Components: hydraulic actuator operates the ESD valve. Hydraulic control line connects the WHCP to the ESD valve. Pressure transducer monitors the hydraulic pressure in the control line. PLC RTU controls the hydraulic actuator and monitors the pressure transducer. Operation: 1. Normal operation. The WHCP maintains hydraulic pressure to keep the ESD valve open. 2. Emergency shutdown. In case of critical alarms or manual activation, the PLC RTU vents the hydraulic pressure, causing the ESD valve to close. Control loop. Closed loop. The pressure transducer provides feedback to the PLC RTU, which adjusts the hydraulic pressure to maintain the ESD valve in the desired state. Feedback: real-time pressure data from the transducer. Control signal: hydraulic pressure regulated by the PLC RTU. Startup procedure of an oil well. Step-by-step startup procedure. 1. System check. Verify that all control systems, SCSSV, SSV, ESD, are operational. Check hydraulic pressure levels and ensure they are within the required range. Ensure communication with the central control system, HMI SCADA, is established. 2. Initial hydraulic pressure application. Gradually apply hydraulic pressure to the SCSSV control line to open the downhole valve. Monitor the pressure transducer feedback to ensure the valve opens smoothly. 3. Surface valve activation. Apply hydraulic pressure to the SSV control line to open the surface safety valve. Verify valve position and pressure feedback from the transducer. 4. Flow monitoring and stabilization. Once the SCSSV and SSV are open, allow the well to flow and stabilize. Monitor flow rate, pressure, and temperature parameters through the control system. Adjust choke settings if necessary to control the flow rate. 5. Steady-state operation. Ensure all control loops are functioning correctly and maintaining desired set points. Continuously monitor operational parameters and adjust as needed. Operational and maintenance aspects. Operational aspects. 1. Regular monitoring. Continuously monitor pressure, temperature, and flow parameters. Use HMI SCADA systems for real-time data visualization and control. 2. Alarm management. Set appropriate high and low alarm thresholds for critical parameters. Ensure alarms are promptly addressed to prevent system trips or failures. 3. Manual overrides. Provide manual override capabilities for emergency situations. Train operators to use manual overrides safely and effectively. Maintenance aspects. 1. Preventive maintenance. Schedule regular maintenance for hydraulic systems, actuators, and control components. Inspect and replace worn or damaged parts to prevent failures. 2. Calibration. Regularly calibrate pressure transducers, temperature sensors, and flow meters. Ensure accurate and reliable data for control loops. 3. System testing. Perform routine testing of ESD systems to ensure they function correctly. Conduct periodic pressure tests on hydraulic lines and actuators. 4. Documentation and training. Maintain detailed records of maintenance activities and system modifications. Train personnel on system operation, maintenance procedures, and emergency response. Conclusion. The control loops within a WHCP for SCSSV, SSV, and ESD valves are designed to ensure safe and efficient well operations. By employing closed-loop control systems, these loops provide precise control and real-time monitoring of critical parameters. Proper startup procedures, regular monitoring, preventive maintenance, and thorough training are essential to maintain the reliability and safety of the wellhead control systems.